Hello. Today's topic is pretty complicated, so it may take a couple of views, but we're going to start off with relative motion. And then we're going to go to something a little bit more current after that, so relative motion. Now, relative motion kind of deals with motion, how things look like they're moving due to perspectives. So, the first example is this. When you're in the subway, and you look to the person who's maybe sitting next to you, maybe across the way, the person standing in front of you, to you, that person doesn't appear to be moving. Because from your position, from your perspective, that person isn't moving. But if you're going to look out the window, you'll see people on the platform maybe as they go by, and they will appear to be moving. So, motion, or at least how motion is perceived, is very important about where you are compared to that motion. When you're in the subway, you're moving with the subway. The person in the subway with you does not appear to be moving. Meanwhile, if you were outside the subway looking in, you could clearly see that that person's moving. So let's see an example first. Let's go back to the subway. So let's say here we are in the subway, and we have a very angry student. Maybe he's, just frustrated. He's got stinky lines. Maybe he is unhappy about having BO. Who knows? And let's say he sees his arch nemesis, Mr. Shaw. So here's Mr. Shaw. He's a pretty tall guy, pretty handsome if you ask me. He's also got huge muscles. Yeah, that's Mr. Shaw. There he is, Mr. Shaw. Now once again, they're both on the subway, so when they look at each other, they would see each other not moving. Now let's say the subway though is moving. Let's say it's moving this way. Let's adjust that just a little bit. Let's say it's moving this way, and let's say it's moving at 15 meters per second. So here we are, we're on the subway, here's the angry student, and there's Mr. Shaw, and the subway together is moving 15 meters per second. Now, Mr. Shaw starts to read maybe the paper, and the angry student somehow finds a rock. He's going to throw it at Mr. Shaw. So here's the rock, and let's say he's going to throw this rock. Let's try to make the vectors to scale. He's going to throw this rock at Mr. Shaw, and it's going to be moving at 5 meters per second. Now, let's take a look once again from everybody's perspective. Now, the angry student, he's going to throw the rock and it moves away from him at 5 meters per second. Now, Mr. Shaw is going to see the rock coming towards him at 5 meters per second. Now, that's everyone in this position's perspective. But let's say you are on the platform. You are at a station and you're just reading, standing there, doing your homework, and suddenly you look up and you go, "Hey, Mr. Shaw's on that train," and there's an angry student throwing a rock at him. Now, let's ask ourselves, our student, he sees the rock moving at 5 meters per second, he's on the train. Mr. Shaw sees the rock moving 5 meters per second, he's on the train. You are off the train. You're not on the train. You're looking in through the windows as the train goes by. What do you see? Well, the interesting thing about relative motion is it's very similar to what we've been doing in class. It's simply vector addition. We add vectors together head to tail, and you standing outside the train, will actually see the resultant of these two vectors. So you will see a ball moving to the right at 20 meters per second. So once again, the train is moving 15, the ball is moving 5. You being an observer who is, let's just say, once again, let's clarify, you're at the train station. You're what we call in the business stationary, meaning when you're stationary, your velocity is equal to 0. You look into the train and you will in fact see, or you will see the train going by and you'll see the ball pass you by going 20 meters per second. Now let's take just one more quick example. The same exact thing, but let's change it just a little bit. Now this time, I'm not going to change how fast he throws it. I'm going to change the direction of the train. Before, the train was coming from the left and going to the right. Now the train is going to be coming from the right and going to the left. Now let's ask, how fast is this train traveling? Let's change the color of this real quick. that wasn't as awesome as it was before. There we go. That happened. Now when we add these vectors together, which vectors? These vectors. We'll see that now we're going to get subtraction. We should get a vector that's going to be 15 minus 5. And hopefully you're doing some real quick arithmetic in your head, and you'll do 15 minus 5. You will see a rock traveling at 10 meters per second, and it's going to the left. Now you're saying, whoa, 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 he's throwing the ball his right, towards Mr. Shaw, but it actually, from the perspective of me outside the train, I'll see it moving left. Yes, the train is traveling that fast. The train is traveling much faster than the rock. So therefore, you will actually see the whole incident moving to your left. Now you may say, well, if I see the rock moving to the left, how will it ever hit Mr. Shaw? Well, Mr. Shaw is traveling to the left too. And you can see that the ball is traveling to the left at 15 meters per second, or 10 meters per second, I'm sorry. The ball, or the rock, is traveling to the left at 10 meters per second. How fast is Mr. Shaw traveling to the left? Well, he's traveling to the left at 15 meters per second. So that's how the ball, the rock, is going to hit Mr. Shaw. And this is relative motion. Again, from these guys' perspective, no matter how the train is moving, they will see the ball going towards Mr. Shaw at 5 meters per second. But depending on how the train is moving, the observer, you, outside the train, will observe a different circumstance. Now let's back up again. We're going to get rid of some stuff. Up. Yeah, let's do that. Okay, so let's talk about our really advanced topic of today, and what the question was really about, and that is relativity. Control C. Relativity. So, and to be actually very specific, we're talking about special relativity. And special relativity deals with the speed of light. It says the speed of light, oh my goodness. One of those days. The speed of light is constant no matter how it is observed. Sorry about the terrible handwriting, I'm kind of in a hurry. So, the speed of light is constant no matter how it is observed. Very good. Okay, let's go back to the train. Let's say our student no longer has a ball. Let's say that they now have some kind of laser. So here's our laser. It's like maybe a box that you can, in fact, shoot light out of at a high enough energy level that it's going to maybe injure Mr. Shaw somehow. So it's going to shoot a laser this way towards Mr. Shaw. Now, if you don't know, light travels very fast. And in fact, how fast does it travel? Well, that's a good question. It travels at 3 times 10 to the 8th meters per second. So that means if you're outside the train and you look in, you will see some interesting things. So, first off, what does the angry student see? He sees light traveling away from him at 3 times 10 to the 8th meters per second. Now, he's probably never going to be able to observe that, but let's just say he can. And Mr. Shaw, he'll observe, even though it's not very practical that he can, he'll observe light coming towards him at 3 times 10 to the 8th meters per second. Now remember our rule of special relativity. The speed of light is constant no matter how it is observed. So here we have two people that are in the vehicle. How do you observe light? Now you may want to say, Mr. Shaw, you add the vectors. So I would take these vectors and add them head to tail. Now this one right here would need to be much, much longer. But I don't have that big of a page to draw it. So the trick is that you don't add the vectors for light. You will not take this vector and put it like so. No, 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 no. Because then you'd make a speed of light that's faster than how somebody else observes it. Light can only be one speed. So how fast do you see light traveling towards Mr. Shaw? You'll see it the same speed that Mr. Shaw sees. And you'll also see at the same speed the angry student sees. No matter what happens to the speed of this train, let's just say the train is no longer traveling that speed. Let's say it's traveling 1.5 times 10 to the 8th meters per second. That's half the speed of light. So if the train is going half the speed of light and the light is traveling at the speed of light, you would say we just simply add these together and you would get 1.5 times the speed of light. No, 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 no. Because once again, how this guy observes light and how this guy observes light must be the same way that you observe light. So light, no matter where you are, travels at 3 times 10 to the 8th meters per second. It's kind of a universal speed limit. Nothing until last week could travel faster than light. And now it's a big deal, because what's going to happen? Nobody knows. We're going to have to rethink 100 years of physics. So it's very, very fundamental shift, and it's very profound. So stay tuned, because physics is a constantly evolving, constantly changing science. Thank you for tuning in.